Okay, so thank you once again to Matt for waking up very, very early to give us this talk. We were talking earlier about how much we enjoyed the previous talk. So yeah, without any further ado, I would say please take it away and talk to us about jet drift from collective flow. Thanks.
Fantastic. Well, thank you guys for having me back. It was a real pleasure to talk to you. Last time I gave sort of a general overview colloquium type talk about hot QCD and cold QCD and how one uses the two of these things to try to learn something about the internal structure of the proton. This time I want to focus on a particular sector of that discussion and pick out hard probes and jets, and then tell you about a series of recent papers that I've been working on since before and now after starting at NMSU and bringing our students into the mix. So let me start off, of course, by giving a shout out to the students. These are the ones who I want to advertise as widely as possible. There are three main papers that are the subject of the discussion today. The first one is a 100-page theoretical paper with myself and my collaborators and former collaborators from Los Alamos National Lab. In particular, these are Andrei Sedefiev and Ivan Vitev, my former postdoc advisor when I was at Los Alamos. We wrote this paper, which extends the formalism for jet interactions with the medium beyond leading power in the jet energy. And we included corrections that made it sensitive to the transverse momentum of particles in the medium. So we derived this big 100-page paper, and then at the end of it, we got relatively simple expressions for the momentum distribution of jets, the medium-induced radiation of jets, and we needed to understand the implications of those results. And that was a great opportunity for my students to get involved when I started at NMSU. We took sort of the key results, the line integrals that come out of this calculation, and we started simulating them just to understand what the physics was coming out of this calculation. We started with very simple toy models and then have slowly moved our way towards increasingly realistic heavy ion collisions. And the stuff that I'm really excited to show you at the end of the talk today involves state-of-the-art 2+1D viscous hydrodynamic simulations with the jet simulated on top of them. So I'm very excited to show this entire storyline. So I thought I would start off by recapping some of the things we talked about last week to zoom in on a particular region of the QCD landscape. So just as a reminder, we talked about the basic paradigm of heavy ion collisions. The standard model, you might call it, of heavy ion collisions describes two colliding nuclei. So typically one looks at, say, gold-gold collisions at the at RIC or at lead-lead collisions at the LHC. At the very early times, the two colliding nuclei are highly Lorentz contracted due to special relativity. Their width is essentially contracted down to a delta function so that they're a sheet of energy density colliding with another sheet of energy density. Nobody really understands what's happening in that first femtometer over C worth of time. But what is well understood is that by about 1 Fermi over C, the energy which was contained in the colliding nuclei has approximately, I don't know if thermalized is the word that I want to use, hydrodynamized, at which point from here on out, whether it's in thermal equilibrium or not, it's well described by hydrodynamics. So typically the ingredients of heavy ion collision are some ansatz for the initial conditions, and then you have to try to constrain that as best you can. Some transport parameters associated with the quark-gluon plasma phase. Those transport parameters include things like the viscosity. They also include all the information about the equation of state. And then as the plasma that you create at very early times and very high temperatures expands and cools, it eventually crosses the QCD phase transition. When the temperature falls below the crossover temperature, then your degrees of freedom change from being individual liberated quarks and gluons that are free to move around the plasma into bound hadrons, protons, neutrons, pions, that for a finite period of time continue to rescatter off of each other in a non-trivial way before eventually the density just becomes so low that the particles no longer see each other. And then you end up with individual particles that move along straight line ballistic trajectories. This is referred to as freeze out. And then from there, the particles are picked up in the final state detector. The soft sector of the plasma involves looking at the particles with low momentum that are produced that make up the plasma itself. And there you have an interesting competition, an interesting game of trying to map back the final state particles back to something like the initial state energy densities and or transport parameters of the plasma. This was what one of our students in our group referred to as nature's Fourier transform, the effective mapping by the physics of the plasma between whatever shape of your initial condition you have and whatever final momentum distribution of measured particles you have. The statement was that in the soft sector, essentially, however elliptical your initial state in geometry is, translates directly into how elliptical your final state momentum flow is. And likewise for the higher Fourier harmonics, however triangular your initial state is, that directly maps to how much triangular flow there is in the final state. And that's both a good thing and a bad thing. It means that you're not incredibly sensitive to, well, it means that the effect of the plasma is particularly simple, but because the effect of the plasma is particularly simple, it means that you're especially sensitive to your assumptions or choices of those initial conditions. And so then one has sort of the inverse problem of trying to deconvolute information in the final state out of these two sources, the initial condition and then the effects of the plasma itself. While the physics of the plasma is complicated, there are a number of very simple signatures that emerge. The simplest of these is the centrality, which we talked about last time. Experimentally, centrality is just a way of counting the number of particles that are produced. It doesn't even matter what units you use to measure them. It doesn't matter your overall systematics. It just matters the relative dependence of how many particles you lose as you go to a more and more glancing collision. And the thing that's so useful about this is that there's a strong correlation. In fact, for a smooth, simple model of the density, like an optical Glauber model, that correlation with the eccentricity is completely linear. So that there's a perfect mapping between how elliptical the event is, that's this vertical axis, the root mean squared value of that ellipticity epsilon 2, with the centrality itself. So this is exactly what's illustrated here in the cartoon. If I actually calculate it, let's say, in a model where one of these things is assumed to be a Gaussian, and I calculate that overlap, then that's what substantiates this very simple mapping. And that's a powerful tool for the experimental analysis because number of particles is a very easy observable to select on. And then just by choosing different centrality ranges, different percentiles of that multiplicity distribution, you're effectively selecting on events that have different levels of ellipticity. So you have a very good experimental control on the shape of your event. And this paradigm is sort of what leads us to the canonical signatures of forming the quark-gluon plasma. There's one set of signatures that are associated with the soft sector, in particular, the onset of collective flow, where it's not just two particles going in a correlated direction, but all of them. And then the flip side is for the hard sector, for particles that have energies way above the energy scale of the nuclear plasma itself. Those particles are not a part of the plasma. They're more like foreign objects that are penetrating through the plasma. And so those provide information on the stopping power of the plasma. So this is an example of a dijet or a dihadron event that's created somewhere in the middle of the plasma. You see one of those particles escapes with a high concentration of energy in a relatively narrow angular window, whereas its counterpart that was initially back-to-back to it or close to back-to-back to it is broadened. You see that the size of the cone has increased and overall the energy is decreased so that the total amount of energy which is contained in these calorimeter towers is less than the total amount of energy contained in those calorimeter towers. And there are a couple of different important effects that are reflected in this. The transverse momentum broadening or deflection of the jets relative to each other, the transverse momentum increase of the envelope of the jet, and the energy loss of how much energy is contained within the relative jet cones. So these are sort of the two subsectors of the hot QCD field, really talking about the soft sector of the plasma and collective flow, or the hard sector where you're looking at high energy particles that are penetrating through the plasma and being modified as they do so. That's the sector that I really want to zoom in for the talk today. So jets themselves are complicated enough anyway, even in vacuum, but what we want to do is something even more audacious. We want to use the jets as probes of how the medium is modifying them. So that's not only a complicated measurement, but a difference of two complicated measurements. So to start off with, it's a highly non-trivial question to talk about what even is a jet. The theoretical perspective that I'm going to take on this slide is that a jet is a microcosm of QCD. A jet essentially is what we see experimentally when we initially create something that is made out of quarks or gluons, made out of partons. So the simplest of all canonical examples of this is electron-positron annihilation. In addition to purely electromagnetic processes like E plus E minus goes to mu plus mu minus, there are, let's say, semi-hadronic processes where E plus E minus annihilate electromagnetically, but then the particles that they create can be QCD particles. So if they create a quark and an antiquark, the initial quark and antiquark are receding from each other at the speed of light, each one containing square root of s, the center of mass energy contained by the E plus E minus pair. And then as they recede, the jets undergo a huge amount of scale evolution, everything from it being initially produced at a very high momentum scale, q squared. In the case of E plus E minus, that high momentum scale q squared is equal to the center of mass energy s of the E plus E minus pair. And then as the quark and antiquark recede from each other, they undergo a cascade of radiation, ordinary QCD vacuum-like radiation. And so that turns something that is initially a quark-antiquark pair into a quark and an antiquark plus some gluons, plus some more gluons, plus perhaps more quark-antiquark pairs. And every time the jets radiate more and more particles, they diffuse some more of that initial virtuality. The jets are initially created very far from being on mass shells. So even though you have a quark and an antiquark here, they have way more energy than they're allowed to have. And they need to diffuse that energy, diffuse that virtuality away into many particles before they can finally go on shell and become real particles with infinite lifetimes that eventually reach the detector. And that's essentially what's happening here, is that you're going down in scale from something initially that's very high energy, very hard momentum scales, and then it bleeds away some of that virtuality into more and more particles, and the relevant momentum scale decreases until eventually the typical scale of particles in your jets reaches the confinement scale, lambda QCD, something in the neighborhood of 1 GeV or so. Again, nobody knows exactly what happens to the jets as they undergo the hadronization transition. That's sort of the deepest mysteries of QCD. But that's part of what makes jets so powerful, is that what we aim to do in constructing and defining jets is to define an effective field theory object, something which actually counts how much energy fell within a particular radius, as opposed to outside of it, with certain defining cuts, like a radius cut, an energy veto cut, things like that. And if we define it correctly, which is a very non-trivial task, then we can establish a mapping between things that I can calculate in theory, in particular, production of particles that are initially just individual partons, and then something that describes how those partons change in QCD, and then actually map it onto an observable that includes all of that late time hadronization physics. That is a very audacious program, even for jets in vacuum, but it can be done. This is not exactly my area of expertise, but there are well-defined effective field theory methods that define jets as effective degrees of freedom with a particular radius, with a particular energy veto, and you can map back in a perturbative sense in a well-defined way that says a jet equals a single quark at leading order, and then order by order in perturbation theory, if you want, you can calculate how this successive pattern of radiation changes what's in a jet, depending on whether or not these emissions fall inside the jet cone or outside the jet cone. So it's complicated, but it's doable. The essential structure of a jet in vacuum comes from the vacuum emission probabilities of QCD, and these are fundamental universal building blocks of QCD. The essential physical mechanism which is responsible for the vacuum structure of the jet is vacuum radiation, primarily the emission of gluons, especially soft and collinear gluons, let's say soft and collinear gluons for a particular range of energy and transverse momentum phase space. These elements that build up the vacuum emissions are referred to as light front wave functions. That's sort of the elementary building blocks. Really at the amplitude level, it describes the amplitude for something that at time minus infinity was a single quark, to by the time it reaches time equals 0, fluctuate into something other than a single quark state. This is what my advisor's advisor, Al Mueller, refers to as old-fashioned perturbation theory. It's literally just time-dependent perturbation theory, but now you're using as your time the light front time, the relevant time scale for a particle moving at the speed of light, which goes exactly as far along the z-axis as it does going forward in time. And if you just rotate your coordinates, you redefine what you're going to call time. This is just an ordinary time-dependent perturbation theory amplitude for an initial state to transform into a particular final state. So the building blocks of all of this physics are actually quite familiar to us. When you compute this light front wave function, the square of that light front wave function is a probability density. That probability density has a very important name. It goes by the name of the Altorelli-Parisi kernel, or perhaps the DGLAB kernel. That's exactly this. This is that radiation probability for a particle to emit or to split, to undergo a branching into a particular final state. And then when you calculate that wave function squared, you find that it has a particularly interesting dependence, particularly interesting distribution for the case when you're radiating a gluon. The momentum dependence goes exactly like 1 over k squared. And that's very convenient because then when I integrate over the phase space of that emitted gluon, the integrand becomes logarithmic. You have something which is a 2-dimensional integral over the transverse momentum, and the function has a 1 over k perp squared dependence. So when I do that integral, I naturally get something which is a logarithm. It's a logarithm of whatever the maximum momentum scale is divided by the minimum momentum scale for which my approximation makes the integrand logarithmic. And basically the range where this works is anything which is much greater than the typical mass scale or other momentum scale present in the branching. And it goes up to the maximum allowed hard scale in the problem. The energy dependence is much more interesting. So this comes from the approximation that the splitting is hard, that whatever amount of transverse momentum p perp I have coming in here, that's totally negligible compared to a huge back-to-back recoil in this k perp variable. The other approximation, which really only holds for soft gluon emission, is the approximation that the gluon energy here is much smaller than the energy of the parent particle. If you have both, then not only do you get the 1 over k perp squared for the transverse momentum factor, the energy dependence of the wave function squared also goes like 1 over omega, omega being the energy of the gluon. So this particular form comes from gluons that have both a hard back-to-back branching, that's sort of the essential physics of repeated DGLAB splittings, or the repeated splittings of this type, and the 1 over omega, which comes from specifically the soft gluon emission. In the region where you have both gluon emissions that are sort of hard back-to-back emissions, and gluons that are, let's say, longitudinally soft, that carry a small fraction of the momentum, for that, you get not just 1 log, but 2. So this doubly logarithmic phase space is what defines the most important range of gluon emissions, the most important type of gluon emission that makes up this vacuum-like emission. And what you see is that this double logarithmic emission has each branching much harder than the one that came before it. That allows you to ignore whatever history this particle came in with. And here, all that matters is this local back-to-back splitting. Those approximations essentially decouple this one branching from the history before and after it. And that's very nice. That essentially reduces this multiple branching history into something which is semi-classical and Poissonian. So that in this region, where each gluon emission is independent of the one that came before it, you have this simple probabilistic, even Poissonian distribution. And the nature of the emission has a particular structure to it, because you're saying the most important, the dominant contributions to this probability satisfy this logarithmic power counting. And you can easily keep track of what conditions define when you do or don't get that double logarithmic enhancement. And the conditions when you do get the double logarithmic enhancement are referred to as angular ordering. This condition where each emission has much lower energy but much higher transverse momentum than the one that came before means that the angles successively increase as you go to later and later branchings. Was there a question so far?
Wait, I'm sorry, the angle is decreasing, right?
Did I write it backwards? Transverse momentum is increasing as you go to successive DGLAB splittings. Energy is decreasing. Apologies if I fumbled something here. Maybe we can talk about it afterwards.
So qualitatively, the last splitting is the widest or the narrowest?
I think the last splitting is the widest according to my conditions for multiple DGLAP emissions. Maybe I'm confusing something here, thinking about PDF DGLAP evolution as opposed to fragmentation function DGLAP evolution. This is definitely the picture where I say I'm going to measure, let's say I measure this quark in deep inelastic scattering. And then I say the thing that I measured at this scale came from 1 or 2 or 3 much harder branchings than the ones that came before it. To be honest, I'm always a little bit fuzzy about some of the translation between initial state and final state pictures of DGLAP. So apologies if I've said something incorrect here. Should I go on, or do you want to discuss this point further now, Will?
I think somehow maybe I was confused, and somehow in my mind I was thinking it gets lower, but I think certainly what you have written at the bottom is it gets wider. And I think
yes.
Now that I'm sort of thinking about it again, isn't it that you could also think about it as that there's interference, that if you want to, so the first emissions are small angles, and then for the next emissions to not be destructively interfering, they have to be wider at some point.
Oh, perhaps if you're talking about LPM, then perhaps that's a different story. I'll get to LPM in a minute. Right now, I'm just talking about vacuum-like emissions.
I was also talking about the vacuum, yes.
Oh, you're also talking about vacuum.
Yeah, and in fact, you say talking in branches, so it's an independent emission from each branching is independent.
So let me see if I can hammer this out now before I say anything else that's wrong. What I have in mind is this, that DGLAP ordering, if I have a branching like this, and then I've got some successive branchings that come later. My condition here is that my K-perp squared be much greater than my P-perp squared. That's necessary in order for me to ignore the history of whatever came before and then get an independent kernel of this type. Right. And then if one has small x as well, this is not necessary for DGLAP, but it is necessary for the double log, then you would have, let's say, omega-1 much greater than omega-2, much greater than on down the line. And I think my angle is approximately K-perp over omega. And so this is where I end up saying my numerator is increasing as I go down the line, my denominator is decreasing as I go down the line, so I conclude that my angle is increasing. But again, I'm always a little bit fuzzy on whether I've made the analysis correctly and translated it to a final state. Do you agree with what I've said here? Okay. Please do interrupt me if I say something misleading or not quite accurate at any point. Okay, let me try to clear the screen. Erase all ink on slide. Okay. Right, so I mostly wanted to give some motivation or some basic physics understanding as to what the structure of a jet looks like in vacuum. The jet is, like I said, a microcosm of QCD that describes everything from the very hard, very perturbative physics at high Q squared, all the way down to the very non-perturbative, unknowable physics at Q squared of order the confinement scale. And mostly in between, that shower of particles that you get is described by this quasi-independent Poissonian branching with a very particular structure that comes out of it. So jets in vacuum are already quite complicated enough. This is just a theorist's sort of idealized perspective on what a jet is supposed to be in order for me to make a matching onto it between something I can calculate and something that I hope is measurable. The flip side of that is what is measurable and how do you actually construct a jet experimentally? So from a theory perspective, I would say jet is this effective field theory object that encodes lots of structure about QCD. Experimentally, a jet is defined by an algorithm. It's a way of clustering particles together to define what you call a jet, something that has a certain total energy, a certain total momentum, and it's defined by certain cutoff parameters on its phase space, usually a radius and potentially an energy cutoff. But there are, of course, many different ways to do that. And the way that they cluster different particles together leads to different jets. So this is an example of one event with particular particles produced in the final state, and then the effect of running different jet clustering algorithms on it. And you see from the different color patterns how it has gathered up different particles in the event and assigned them to belong to one jet or another jet. And you can see just by eye that depending on what assumptions you make, what algorithm you choose, you reconstruct the same event very differently. So this is one of those takeaway messages that I always remember in the back of my head from my good friend Rosie Reed. Different jets are different. Experimentally, when they reconstruct a particular set of jets and they say, I'm running anti-KT algorithm using radius of 1, that produces jets with a particular structure. But then if somebody else takes their analysis and say, well, I'm running Cambridge-Aachen, that produces jets that are very different. And the jets that are defined by this algorithm are not necessarily comparable with jets that are defined from that algorithm. So it's very important to have sort of apples to apples comparisons between what you want to calculate theoretically, what you can calculate theoretically, and what you would like to map onto experimentally. Thankfully, the thing that I'm extremely grateful for is that in this effective field theory framing, you can define an effective field theory object that satisfies these criteria, that reduces down to a delta function telling you I had just my jet equals a single parton initially, and that includes that successive radiation perturbatively and can potentially be extended to something non-perturbative. So there is a good effective field theory way to define this mapping, but I want to impress upon you how complicated it is. At low orders in your perturbation theory, for a small jet whose radius is in theory much less than 1, but in practice you can push it up to about 0.4 or something, you can nicely show that the differences between different algorithms are small. As long as you focus on very narrow jets that are highly concentrated around a few particles, these differences are not important. So there is a systematic way that you can define, to at least control in principle in the theory, where I need to worry about the differences coming from different jet algorithms and where I don't. So that's jets in vacuum. Jets in vacuum are already complicated enough. But what we really want to do is use jets as a probe of a nuclear environment, especially something like the quark-gluon plasma, which is not stable and which is formed only for a brief period of time. Here, this involves asking how much that pattern of emitted radiation from the jets is modified because the jet is now moving through an environment. In vacuum, we said that those multiple emissions are described by this Sudakov factor, this doubly logarithmic phase space, which is quasi-Poissonian. In medium, the modification of that interference pattern due to, let's call it, shaking the jet or accelerating the charge as it moves through the medium. This is referred to as the LPM effect. That stands for Landau, Pomeranchuk, and Migdal. They looked at this effect first in QED, the abelian version of this in-medium energy loss. And the thing that we're talking about now is the non-abelian generalization of the LPM effect. And this problem is in general a very complicated one, because you're asking essentially an interferometric question about the overall intensity of gluon radiation that's produced due to a combination of whatever quantum mechanically happens in the amplitude. This is represented as whatever's to the left of this final state cut, and whatever quantum mechanically happens in the complex conjugate amplitude. And they don't have to be the same thing. This is, on one hand, very nice, very powerful, because the final interference pattern which is produced is a superposition of many different factors that carry information about the medium that you pass through. This, in principle, carries position space information about the location of charges or the location of scattering centers and the density thereof as the jet moves through the medium. It also contains momentum space information associated with the particular momentum of gluons that are absorbed as the jet passes through the medium. And that final interference pattern is a really interesting and complicated superposition of the two. It's an entangled mixture of these pieces of information. And ideally, what we would like is to make a measurement of that final state jet distribution, and then infer something about these position and momentum dependent quantities. The essential framing of all jet theories, there are many different versions of jet theory, but they all essentially rely on a separation of scales that allows you to define what is the jet versus what is the medium. So I would say the 0th order starting point for any of these approaches is the separation of scales. E, the energy of the jet, or PT, the transverse momentum of the jet relative to the beam axis, is much, much larger than the characteristic scales that are in the medium itself. The nature of the medium changes, of course, depending on what process you're doing. If I'm doing a heavy ion collision, and I think that I've actually formed a thermalized quark-gluon plasma, then if it's thermalized, there's really only one scale. Everything is controlled by the temperature of the medium. So in a hot QCD picture, you would say that the characteristic scale here is the temperature, or maybe it's the Debye mass, which is proportional to the temperature, but it's something set by the temperature itself. The thing that makes it simple, in fact, very powerful, is the fact that if the jet energy is very large, then most of those low energy contributions from this scale don't change the jet very much. For instance, in this limit where the jet energy is much greater than the temperature, the jet doesn't directly lose any energy. It doesn't directly transfer any non-trivial amount of its energy to the medium or absorb any comparable amount from the medium. That's just a consequence of expanding the kinematics where mu over E goes to 0. This is referred to, by the way, as the eikonal expansion, the eikonal approximation, where you're effectively taking the energy of the jet to infinity. This has a lot in common, by the way, with the physics of small x, the physics of usually cold QCD when you're talking about gluons that are being emitted from very high energy particles. So mu over E is the relative separation of scales between the jet and the medium. There are also a few other scales that enter the problem that control the physics. One of them is the typical distance between scattering centers, or between interactions in the medium. So this delta z, the typical distance between scatterings in the medium, is a number of order the mean free path. So that's one way of talking about this. And you get a very different picture of how the jet interacts with the medium depending on whether that mean free path is very long or very short. If the mean free path is fairly long, if it's comparable to the length of the system, then the jet travels significant distance between interactions. And that large distance between interactions makes you very sensitive to the details of all of the phases. So you have some phase of the wavefront at this point, and you're very sensitive to exactly how much the phase of that wavefront changes before the next scattering. The opposite limit is the one where the mean free path is very short compared to the size of the medium. If the mean free path is very short, then the jet is essentially scattering all the time. And then you have almost a smooth, continuous, non-stop scattering, or like a quantum mechanical continuous measurement problem, where the jet is interacting all the time. And there you're getting gluons that are emitted that don't necessarily care very much about how the phase changes between each scattering. They're instead dominated by a bazillion very soft scatterings. So this is sort of the underpinning of whatever approach to jet physics you like. There are specialized approaches that deal with the limit of large and small opacities. The large opacity limit is the one for a high density plasma with a very short mean free path. This usually goes under the framing of like path integral type methods. This is what's referred to as BDMPS, named after the authors Bayer, Dockschitzer, Mueller, Pena, and Schiff. Path integrals are nice, and I think, to the best of my understanding, that the path integral that they set up for the high opacity limit is in principle exact, that it contains all number of scatterings, no matter whether they're high opacity or small opacity. The problem is that I can write down a lot of path integrals, but I can't actually calculate very many of them. The only one that I can actually evaluate is a Gaussian. So while in principle, the beautiful path integral that they write down for this high opacity limit could be exact, you can't use it exactly unless you find a great way to evaluate every possible path integral. Instead, you effectively have to shoehorn it and force it to become a Gaussian. And that's really where the more severe approximation comes in. To actually really use this stuff, you have to assume that it is not just resummed, but very, very dense. That Gaussian approximation that makes the path integral tractable is valid in the limit of a very, very dense plasma, sort of density going to infinity, but not really anywhere else. That's exactly the opposite of what you get if you take a perturbative approach to this calculation, where you're sort of expanding order by order in the number of scatterings in the medium. The typical number of scatterings in the medium is just the length divided by the mean free path. That number is called the opacity. So one perspective, the one that I will follow here, is an opacity expansion approach, where it's assuming that this number is small, and that justifies a perturbative expansion where I can calculate order by order in 0 scatterings in the medium, 1 scattering in the medium, 2 scatterings in the medium, and so on. So that's sort of diametrically opposite from this high opacity formalism. The ingredients which build up that final state interference pattern are complex phases, and they come essentially in 2 different types. depending on the history of how the jet propagates through the medium and when the gluons are emitted, you accumulate different complex phases from that history. So two different types of phases can show up. One of them comes from the boundedness of the emission time. So if I had a gluon that was emitted anywhere between time minus infinity and some particular time, then I would integrate the emission time of that gluon from minus infinity up to some time. And if one of the limits is infinity or minus infinity, then when I integrate, I get zero. The boundary condition just goes to zero. And in that case, you get a complex phase, but then you take the absolute value squared and it doesn't have any consequences. But if you have a gluon emission that's bounded both above and below, now when you integrate the emission time, you get a difference of two finite terms, one of which describes effectively the phase of the wave as if it was emitted from the lower limit versus the phase of the wave as if it were emitted from the upper limit. So this finite emission time effect leads to a subtraction, a difference of two complex phases that's sensitive to the difference between those 2 points. The other kind of phase that you can accumulate is an instantaneous phase slip. Essentially, it's a change in the wavelength of a particle. That can happen if you have a scattering in the medium that, let's say, redistributes momentum between multiple particles in the jet. So this is an example of a double scattering that doesn't transfer overall momentum to the jet, but it could subtract a certain amount of transverse momentum from one particle and give it to another particle. So even though there was no net change in the overall direction or energy of the jet, by redistributing momentum among the particles, you change the wavelengths. And if I instantaneously change the wavelength of the emitted gluon, then I cause a phase slip, essentially between the wavelength on one side of the point and the wavelength on the other side of the point. So I would say these are the elementary ingredients that one uses to build up the answer, build up the final interference pattern. And the result includes summations over lots of diagrams. Here, this is just an illustration of an even simpler process. Here, I'm really talking about the induced radiation. To fit it all on one slide, if I show you not the radiation case, but just the transverse momentum distribution of jets case, you see that you have to add up all possible interactions with the medium at a given order. So this example says, suppose I have a 0th order in opacity contribution. This just describes how the jet is produced without scattering in the medium. That's 0 number of rescatterings. If there are 0 re-interactions with the medium, then this is just my initial distribution. This is however many jets I had that came out of the hard scattering that created the jets in the first place. It is industry standard to assume that you can make a factorization of the hard process that created those jets from whatever those final state scatterings are that come afterwards. That's a seemingly reasonable assumption to make, but there's potentially a lot of devils in the details there. And that's something that Will and I have been looking at in detail recently. But for the moment, let me leave that aside and carry on in the usual approach. So the usual framework would say I have basically just some function. I call it J of P at the amplitude level. You could call it some cross-section or some number distribution at the amplitude squared level. What you really care about is how this is modified when I now put in one scattering in the medium. That's one scattering at the level of the amplitude squared. And as anybody who's done quantum mechanics knows, there are 2 different ways that you can do that. You could have an order G correction in the amplitude and then square it. These are so-called real corrections. My former advisor refers to these as Born level scatterings, where you have a single scattering and then you square it. But it's also critically important to include the double scatterings at the same order. Even if the amplitude is order G, the amplitude squared is order G squared. And at the same order that you have the square of a first order correction, you also have a quantum interference between a second order correction and the 0th order amplitude. This is absolutely essential because this is how you enforce probability conservation. At a given order in perturbation theory, order G squared overall, I have both this and this. This kind of diagram changes the momentum of the jet. It takes it from something that was initially P minus Q and it produces something that has final momentum P. So if my initial jet is a delta function going in a particular direction, then this scattering broadens that distribution. It takes it from something that was initially a delta function and it moves it out into other momentum states. This double scattering contribution is an interference of a double scattering with nothing happening. If nothing happens, then obviously the jet momentum is unchanged. So this interference process is one where the final jet momentum is identical to whatever it started off as. So if my initial jet is a delta function, this is also a delta function. And this amplitude squared, when you calculate it, is actually negative. That's the critical part. This is essentially telling you whatever probability you add to momentum states that are different than the initial delta function, you have to subtract from the weight of the initial delta function. That's how you do probability conservation, and that's how you ensure that the number of jets is unchanged as you scatter in the medium. So this is just a sketch of what the calculation looks like for a lowest order, a first order opacity calculation for a simple observable. If you want to include gluon radiation, then you also have to include all possible ways, let me sketch it here, all possible ways for the scattering to talk to the gluon. So if I'm interested in the energy loss, the radiation case, then I also have diagrams like this, where the gluon could interact with the quark, or the emitted gluon could be the thing that's scattering in the medium. And you have to do this in all possible ways. So you've got lots more diagrams, things that are before, things that are after, in all possible ways. So you get some sense as to how the calculation becomes complicated. There are quickly, at any given order in perturbation theory, there are many diagrams, and each of those diagrams have a complicated phase structure. And it's important to keep all of that phase structure, especially in the low opacity limit, and use it to compute the interference. So the building blocks of these amplitudes for both the broadening and the medium-induced radiation case are the medium potential and the vertex that describes how the jet interacts with that medium potential. The medium potential is very simple. You can think of it as just given to you by God in some model, but it's really not. It's really calculated from elements of quantum field theory. You can take an incoming particle, an outgoing particle, and ask, what is the gluon potential of that particle? And it's just made up of initial state, final state, a vertex, and a propagator. So you can calculate this. The standard thing that one would do, if you're doing vacuum-like QCD, your gluon wouldn't have any mass. So your propagator would just have a 1/q squared here. If I wave my hands and say something about being in a thermal medium, then I can convince myself that my gluon shouldn't be massless. It should probably have a mass set by the Debye mass mu. The simplest thing that I can do is just take the potential that I would calculate for a vacuum-like particle, and then just give the gluon an explicit mass mu. This effectively is what's referred to as the Julassi-Wong model. This is what you get if you take a vacuum-like calculation, you assume that the gluon is massive and otherwise the structure is unchanged. And this in particular assumes that the mass of whatever you're scattering on the medium is very heavy. It's interesting to note that this simple picture is not the answer you actually get if you do an honest-to-God calculation at finite temperature. There in a hard thermal loop picture, you get something which is similar to this, but not exactly the same. So there's some interesting range of results that you could get depending on what assumptions you make about the medium. For the purposes of what I'm going to show you here, everything that I've plotted in this talk is based on this Julassi-Wong model. We have looked at how much the answer varies as I switch from, let's say, Julassi-Wong at finite temperature to a real hard thermal loop calculation. Things change quantitatively, but not qualitatively. So I can discuss that if you like. So this is one essential building block, which is what is the potential of particles in my medium? The other thing is, how does the jet respond to that potential? And the answer is something really simple. The jet couples to the external potential. The vertex that it couples to here is actually the simplest part of the whole calculation. This is where the Eichenal approximation comes in, where the vertex here depends on the energy of the jet. And if the energy of the jet is extremely large, you pick out basically just one piece, one term of that vertex that dominates. And then you have all the usual propagators and things like that. If you're doing this calculation of transverse momentum distribution in the final state, then these are all of the ingredients you need. If you want to do the radiation calculation, then you have one more ingredient. That's the same emission kernel that went into the vacuum, the same light front wave functions. You can even start off with a diagrammatic calculation that looks like this, and then read off the part of your amplitude that corresponds to the particular light front wave function. So the picture is that this medium potential and that vertex of that potential are dressing up and modifying what is initially this vacuum-like cascade. And by dressing up that vacuum-like cascade, you generate all of these complex phases and you change the interference pattern, the overall intensity of gluons that are emitted. So the structure that you get is complicated. It's hard to write in closed form without some fairly severe approximations. Here is one of those simplest results after making said severe approximations. So this is the result for the, I guess, 6-dimensional distribution of both a jet with overall momentum P and overall energy E, and with a relative splitting that gives a gluon fraction X of the energy and a relative transverse momentum K perp. That double differential distribution is, in this approximation, proportional to however many jets I started off with. That was this picture. So sort of by assumption, by ansatz, I get something out which is proportional to my number of jets that I created. And then this is what describes the modification. There's a momentum integral. The momentum integral integrates over the cross-section to scatter in the medium. That cross-section is basically just the square of this potential. So that tells you how likely you are to interact with the medium. You have an explicit factor that comes from the wave function. This is basically exactly this wave function squared after combining many different terms. You see the familiar 1/k² factor, which is the one that generates the transverse logarithm for the Sudakov factor. Right. You get a complicated angular dependence, by the way, that relates together the direction of the gluon emission, K perp, with the direction of the momentum absorbed, the momentum transfer from the medium, which is this Q perp. And then sort of the most important punchline here is this 1 minus cosine. This 1 minus cosine is the remaining answer that comes from adding up all of those various complex phases. So you see in this limit, if the energy goes to infinity, then the argument of the cosine becomes 0. And then I get 1 minus 1, and the whole thing goes to 0. So this answer contains within it an interference pattern that requires the gluon to have been emitted in the medium. If the energy of the jet goes to infinity, then the whole medium just looks like a delta function. The whole medium just looks like a pancake, this. And if the medium has effectively 0 size, then you don't have any room for non-trivial phase accumulation to give you these cosines. So it's a balancing act. There's a sweet spot in between having the energy of the jet high enough that your iconal approximation is good, that you're not sensitive to all the details of the medium, but you don't want the jet energy to go all the way to infinity. There you expect that the effects of the medium should go to 0. This distribution is, yes, sir.
Yeah, what are the bounds on your Q squared or QT integration?
Oh, that's a very tricky, very important question, which Will is more expert in than I am. The answer, as it turns out, is extremely sensitive to what assumptions and choices that you make for the upper limits of these integrations. It is thankfully less sensitive to the upper limit of the Q integration here than it is to, if you integrated the upper limit of the K perp integral there. So one should be extremely careful about assumptions that you make and self-consistency in the calculation when you integrate these things. For specificity, the answer when you integrate this Q perp is that your Q perp max is a number that goes like a square root of the energy and the medium scale here, if I recall correctly. Please fix me if I'm wrong, Will. I think this is right. It's a mixture of these two things that comes from the kinematics of absorbing this much momentum and still needing to go on shell at the end of the day. So the question about limits of integration is an extremely good question, an extremely important question. You can make seemingly reasonable choices for those limits and change the answer that you get 100%. Maybe a related comment to that is that we normally talk about this distribution with the physics of broadening and the physics of stimulated emission in mind. But if you actually plot this distribution, it's not at all obvious that this thing is positive. It's not positive, not everywhere. This was one of the first plots of this result from 2001, I want to say. And notice that the distribution crosses below 0 here. It's perfectly allowed to cross below 0 because this is a difference. This is a difference between number of gluons in the medium versus number of gluons in vacuum. Number of gluons has to always be a positive quantity, but the difference relative to the vacuum could be positive or it could be negative. So there are some regions of phase space, some regions of momentum where this is positive, meaning that you have extra gluon emission relative to what you would have seen in vacuum. There are also non-trivial regions where it's negative, where you have suppression of gluon emission relative to what you would have seen in vacuum. So I just want to impress on you that the physics that comes out of this is much more complicated than the fairy tale that we usually tell, which is a story about energy loss and momentum broadening. While that's true overall, the microscopics, the details are much more.
Another question.
Question? Yes, please.
I mean, all these jet observables that you can define, right? I mean, probably have an impact on what you should be doing here. Have you ever looked at this sort of question?
What do you mean by the jet observables you're looking at?
Well, jet observables, right? There is a whole zoo of different jets, right?
Yes.
And there's a lot of pain going into making sure that they're infrared safe.
Yes,
now,
exactly.
You have other scales in there that might help you on the medium side of things and make you less sensitive to infrared safety than vacuum jets. But since you're comparing both, do you get into trouble with your integral boundaries and other things when you switch from one observable, say, to another?
Yeah, so that's an excellent question and something that everybody in the field should be worried about when you make these comparisons. I think this comparison is safe because the observable that we're talking about here, well, because for one thing, I'm working at a very low order in perturbation theory where I don't have all of the complications of a fully reconstructed jet. The questions that you're asking, oh, let me see where I should draw this, maybe here. The questions that you're asking are especially important when I talk about a reconstructed jet with a particular jet cone radius r. And that's where you're extremely sensitive to the question of when I have one of these gluon radiations, does it fall inside the cone or does it fall outside the cone? Or if I have some energy veto cutoff that says I only include particles if they're above that veto cutoff, then I have the case where the gluon emitted is just above or just below that veto cutoff. So if I'm understanding correctly, I think the question is about sensitivity to those cutoffs that define what a reconstructed jet is. As far as infrared and collinear safety, I know that can be defined correctly. I would probably fumble if I tried to answer the technical questions about it, but that's this effective field theory mapping where you can define a jet function that produces a jet with a given radius and a jet energy veto at lowest order in perturbation theory for small r. That reconstructed jet is just a delta function that reproduces the original quark you have. But as you go to higher orders in perturbation theory, you have to pay very careful attention to those cutoffs on your boundaries. And if you end up with something that is especially sensitive to, let's say, more than logarithmically sensitive to your radius or your energy, then you might be in trouble with something that's not infrared or collinear safe. So the strict answer is that for what I'm talking about right now, I'm doing something so simple that I haven't even encountered this problem yet. I'm not really talking about fully reconstructed jets yet at this level. I'm talking about single particles, individual quarks at this level. So I'm really talking about parton energy loss and parton broadening. But this fully reconstructed jets is absolutely one of the next steps we need to take. And that's where one has to really promote the theory significantly and include these jet functions that are infrared and collinear safe. And if you make the wrong choices about how to do that, you could well find yourself in hot water. Does that answer the question?
Absolutely.
Okay, great, thank you. Right, so admittedly, what we're doing here is quite simplistic, but it lets us access some different physics than what's been looked at before. So we take this as the simplest toy model moving us in this direction. So what I've given you thus far is sort of the standard canonical storyline of what jets are and what the measurements of jets and medium modification should look like. So if the canonical signatures are energy loss and momentum broadening, the canonical experimental measurements that go along with that are jet quenching, the suppression of the number of jets that you produce, and acoplanarities, the relative direction of the jets compared to what you would have expected. How am I doing on time, by the way? I seem to be out of time.
Not great.
Not great. Okay, then. So these.
Well, so let me ask. 'Cause I think there's an empty slot before spring break. I think you're going to. Yeah, but I mean, I think I feel like this has been really great, and we could either try to squeeze things in super short, go all the way till like 3 o'clock, or maybe if you're willing to wake up early again, Matt, we could do a third talk.
Seeing as how I have the slides already, that's maybe not so bad. I'm open to whatever you guys prefer.
You have enough space to cover another talk, another 45-ish. If we keep interrupting you at the same rate.
If you keep interrupting me at the same rate, I think so, yes. And I think I can easily add a couple of more slides between now and the next time, especially if you said spring break. But that's Southern Hemisphere spring break, which is this semester.
Exactly. Yeah. We're on S2 here.
Yes.
Yeah. Look, I mean, I would say we are greedy for your time, Matt. As much as your time you're willing to give us. Yeah.
Well, I would much prefer the chance to talk about it in detail at another date than trying to rush through the fun stuff that my students have been doing now.
Yeah. So do you think, are we at a stopping point, or do you want to give a couple more slides? Should we?
Let me maybe give a flavor, give a motivation of what we're trying to do next, and then we can dive into all the details next time. So I wanted to walk you through sort of the standard storyline of what jets are and how we measure them, in particular to point out the limitations of that. Because the standard candles that one uses are RAA. So RAA is a measurement of the number of jets that are produced with a given PT. It's a ratio of the number of jets that you produce in a heavy ion collision like lead-lead, divided by what you would have gotten if you had just scaled up an equivalent number of proton-proton collisions. So for this observable, a ratio of 1 means that there's no modification compared to what you would have expected in individual PP collisions. And of course, what you see experimentally is that all of the data points in heavy ion collisions are nicely well below 1. This is telling you that you do have jet quenching. You're producing fewer jets at a given energy than you expected. And let's see, for the LHC in a 10% centrality bin at 5 TeV, jet radius of 0.2, reconstructed with a particular jet algorithm, all of those details matter. For those, the suppression factor is about 50%, and it's very weakly dependent on PT. As it happens, everybody's model under the sun can fit this data. Whether you are doing soft collinear effective theory, linear Boltzmann transport, a model called Joule that I still don't know what physics is in it, something else. Basically, everybody's model is cool, to steal a phrase from Jerry Miller, who likes to use that for the EMC effect. The flip side is, if you talk about broadening, momentum broadening is in principle an even simpler observable than this complicated interference pattern stuff. You would like to be able to look at a transverse momentum distribution. So what's being shown here is an acoplanarity distribution. You would expect that your jets are initially produced back to back, something like, this, but they may not be measured back to back. Even if they're created back to back, then they may be measured with some non-zero acoplanarities that are picked up from the transverse momentum of the medium. You can talk about any kind of pairs of particles you want, hadrons and jets, 2 reconstructed jets, 2 particular hadrons. One thing that's very convenient is a photon and a hadron, since a photon does not interact by QCD, so it's more of a clean standard candle of your initial direction. Z's are also used for the same purpose. So whichever acoplanarity you're talking about, you would like to measure the width of that distribution around back-to-back. So here's the angular distribution around pi. You have a peak around pi, and you have some width to it. And what you would like to do is to compare the width that you see in lead-lead collisions versus the width that you would see in proton-proton collisions. And that's a very tricky comparison. There's a lot of backgrounds, there's a lot of unknowns that go into that subtraction to try and compare these things. This is a particular analysis from Elise. I believe it was for 1 reconstructed jet recoiling against a particular identified hadron. You see that the distributions are very, very close to each other here. Here they've used a particular new analysis technique. The main point that comes out of this is that the differences are very small. And depending on exactly how you do the analysis, which data points you fit, you can easily conclude anything from small amounts of positive broadening, small amounts of negative narrowing, or even no change. So it's a challenging spot for the standard observables of jet physics because, yes, absolutely, we see quenching, we see suppression of jets, but that observable is so robust that basically every model under the sun with radically different physics can still get it right. And you have a cleaner observable theoretically in terms of the transverse momentum distribution, but there's a lot of backgrounds. The jets are not perfectly back-to-back even in vacuum, that Sudakov shower creates particles that are not back-to-back. So there's a lot of complicated backgrounds that go into this, and that makes it challenging to unambiguously extract information about jets. The community has very ambitious plans about, I don't know, global analysis, universal extraction of median properties as a function of temperature. But, you know, the skeleton in the closet is that there's a lot of ambiguity about how the theory connects to this data. And I can't tell you how many jet experimentalists have privately told me, I've been working in this field for X number of years. What have we actually learned about jets in that time? And I think this is the reason why. So that is a significant motivation for the work that the students and I were working on, even before that working with my colleagues at Los Alamos. Because the key idea that we were looking at here was asymmetric or even anti-symmetric measures of the jet interactions. So, you know, overall broadening, something that takes a jet cone of a given size and then increases the overall envelope of the jet, that's something which is symmetric. It's an even function. It has no preferred direction. And because of that, it has a huge number of backgrounds, even from the vacuum. But if I ask a different question, if I ask an anti-symmetric question instead of a symmetric question, I ask, what is the net direction that the jets prefer to go? That's a vector-valued observable. That vector-valued observable can never receive contributions from scalar-valued mechanisms that are only able to contribute to broadening, but have no anisotropy baked in, have no particular direction. That makes these anisotropic interactions much cleaner. They have very fewer backgrounds. And in particular, there's nothing in the vacuum that has a preferred direction. So what we were looking at was, in particular, the preferred direction that comes from the velocity or the flow profile of the medium, and how that flowing medium can change a jet going in one direction to give it a preferred direction, to scatter left rather than right. That can happen both at the level of the transverse momentum distribution, like an asymmetric broadening, and it can also happen at the level of an asymmetric pattern of radiation. The fundamental mechanism is essentially the same. We build it out of essentially the same ingredients, but the premise of it is that because these are anti-symmetric effects that require a preferred direction, they are protected by symmetry. These odd observables are totally decoupled from the standard even mechanisms. And that's what makes them promising as a different or new lever into the microscopics of the plasma. Okay, the idea has a long history. We're not the first to think of it. We're just the first to do a real calculation of it. Essentially, what we did was we updated the building blocks. We changed the potential to include the corrections which go beyond the Eikenel approximation, things that go to zero if the jet energy goes to infinity. And we see a large modulation of the potential itself, depending on the velocity of the medium. And essentially what we do is we propagate that forward. We propagate it forward to the transverse momentum distribution, and we calculate the corrections. This is a 1 plus epsilon type correction. And we look at how that leads to a skewness, something that is not exactly symmetric around zero, but has a little bit of a biased tail, so that now if I calculate the average is not zero. And that's the part that makes the difference. So this is what my students have been looking into in great detail. This calculation is the 100-page calculation that leads to this relatively simple answer. And in its simplest form, yes.
Yeah, if you could go back to that last.
Yeah,
picture.
sure.
Can you remind me how this is different than the calculation from, I want to say, Shinyan et al.,
Yes.
where they're looking at, forget what they're looking at that's somewhat different. Could you help remind me, please?
Yeah, they're looking at a very similar observable. This is one of the papers from that group. They're looking at similar asymmetries. They're interested in the ones that are generated by gradients of temperature, gradients of density. That's the other preferred direction that the medium can provide. I think the systematics of that will be qualitatively very similar to the velocity corrections that I'm talking about here, in terms of how they reflect the geometry of the medium and how they can be used for tomography and things like that. But they're looking at gradients rather than velocities. And so for them, the effect is actually probably more important than the effect that I'm calculating here. The effect that I'm calculating here is a sub-iconal correction. So you see that these things are explicitly proportional to 1 over energy. For them, this density correction should not be suppressed by the energy. So they've been looking at similar things. They've been taking a very different approach to the phenomenology. Personally, I think the kind of observables that they were talking about, at least in this paper back in 2020, are barking up the wrong tree. Here, they were clearly looking for something that is a cosine 1 theta modulation, as they nicely show in this plot, something that is like a V1 that would directly skew things left versus right. Our analysis, even though it's built out of very, very similar ingredients, I expect that their results would have or their calculation would have results very similar to ours. What we find when we actually start putting things in an elliptic medium and even in a hydro background is not a cosine 1 theta modulation, but a cosine 2 theta modulation. Basically, the statement is that, yes, the jet gets dragged in the direction of the fluid flow, but the pattern of the fluid flow is elliptical. So it's not correct to expect that you should see an overall like preference for the left direction versus the right direction. It's more that you see a preferred drag of the jets in the direction of the fluid flow, which is itself elliptical. So I think qualitatively, there's going to be relatively few differences between what I show here and what they find in their mechanisms. But they're doing the analysis in a very different way, and I'm not sure they're looking at the most promising signals of this. So this is something that we would like to come back to in our formalism as well. I don't understand anything about what they do in linear Boltzmann transport or how entangled the jet physics is with their assumptions about the medium. So one of the things on our to-do list is now go back and redo the gradient treatment in our language, because we can incorporate that in exactly the same footing as what we've been doing for the velocity corrections here. Does that answer the question, Will?
Yes, you're going along in the right direction. So in particular, if you go back to that nice slide where you had the potential and then also the gradient.
Yes.
Going, please. Sorry, keep going. Yes, here.
Sorry.
Yeah, here. So okay. Yeah, exactly. So on the top part, I at least schematically, we may disagree about the exact potential, but I sort of have a sort of a.
Oh, sorry, my headphones just cut off.
Okay, can you hear us still?
Give me 1 sec to switch the audio output, and then you can repeat your question. Okay, say something. I think I hear you now.
Yeah. So yeah. So with the top part, so this is the hot wind calculation with the ASW folks, and you know you did the full calculation, but at least understand qualitatively. Okay, I have a potential. The potential is shifted due to the velocity flow, and I can kind of map that back to exactly as the pictures you showed in later slides, like the jets being pushed by the medium. So that's then with the gradients, so how do I think about the gradient as similarly affecting the potential, or what?
No, it's not. Well, okay, so gradients affect the potential only through gradients of the temperature, because the potential depends on the Debye mass. So you do have gradient corrections applied to the temperature, to the potential through the temperature. You also have gradient corrections of other factors. So if I go back here, the potential, of course, goes into the cross section. So you have gradient corrections to this. You have gradient corrections to the density. Those gradient corrections to the density couple to interesting like derivatives, momentum type derivatives that can act on the phases that generate the cosines. So the gradient calculation from a first principles point of view, where I think I understand it, comes actually naturally out of the same ingredients. As you're well aware, there's you do some calculation for the amplitude, some calculation for the conjugate amplitude, and then there's a position integral. You have either For the discrete case, you write it like a summation over discrete scattering centers, or you can write it as a continuous integral over a density. That integration over the density involves integrating over the transverse position. The usual way that it's done is you ignore any transverse gradients, and then you get integral d2x. Let me draw it instead of waving my hands. You get integral d2x e to the minus I guess it's q minus q prime dot x perp. And then you've got a density, you have integral dz, and you've got density of z and x perp, as well as other quantities. So the usual way that these things are derived, like the slide here, is you ignore any dependence on the gradients, on the transverse positions, and then this integral just gives you a delta function of q minus q prime. And then you get one q integral as shown here. So this answer uses the fact that the density gradients have been neglected. You don't have to do that. Instead of ignoring density gradients here, you could always just do a Taylor series and keep the terms. The terms that you keep will be proportional to, oh, well, I needed another slide anyway, x perp dot gradient of rho. And the x perp, when you do my integral d2 x perp e to the minus I q minus q prime, this gets translated into a derivative with respect to q minus q prime that then acts on the rest of the expression. So in this long paper in the beginning, we actually calculated, I don't know if we calculated all of them, but we definitely calculated at least for the broadening case, the gradient corrections as well, and that's how they arise. So that's the microscopics of it. If you truncate that derivative expansion, that gradient expansion at some finite order here, you truncate it at some finite order in derivatives, then you end up with something that has, where is it going? Sorry. Yeah, if you truncate it at some finite order, then you end up with finite level of complexity, finite number of derivatives that have acted on those phases. So that's where it comes from, and that's what we would like to try down the line.
So that was very nice, thank you. And while I have used these calculations many times and derived them, one of the somewhat unsettling things in my mind has always been this integral over all d2x perp.
Yes.
Because you're only going out in one direction. And you could say, okay, look, I'm going to take a collection of these jets and then do the average over this collection of jets. But that's different than taking the jet of an average.
Absolutely. And for heavy ion collisions, we know that those fluctuations are important. They are the entire story. This is something that I was uncomfortable with when I was a student working in small x physics and didn't really know any better. And now that I'm a little bit more experienced, I'm really uncomfortable with it. This sort of gradient expansion idea is something that gets used and abused all the time in small x, where we say, oh, I'm working in the limit. Usually we say a to the 1/3 is going to infinity, and I want a large nucleus, a large system size. That's often used to argue that, oh, I don't need to worry about gradients of TB because that should be proportional to 1 over a to the 1/3. That's the usual hand waving that one uses to get rid of it. And that leaves you with essentially a smooth optical Glauber profile. But we know the limitations of a smooth optical Glauber profile. This argument fails because it is only the smooth average density that has a length scale of 1 over a to the 1/3. The fluctuating density in Monte Carlo Glauber retains a non-trivial length scale of order the nucleon size. So it is not this. It is instead, even in AA collisions, 1 over lambda QCD, 1 over the size of a proton. So those neglecting densities, especially neglecting gradients or fluctuations in densities, is something that I think is extremely dangerous and probably has contaminated a lot of important formulas. So going back and recalculating derivative corrections is probably going to be an important exercise. So I'm out of time. I think I've given basically the flavor of what we're after here. The punchline is the students and I have taken this idea, we've taken the results of this calculation, and we have started with the simplest possible toy model and started dialing up the complexity. We started with the age-old brick, although in this case it's a flowing brick, so it's more like a slab of laminar plasma. And we studied the brick. We see a lot of intelligible physics that comes out of it. The next simplest thing we did was we put it in a Gaussian background that at least has some elliptical shape and made simple toy model assumptions. And there we start to see significant coupling of the jet drift to the geometry in a perfectly intuitive way. The picture is very simple. If I have jets produced from the middle, if I turn on all the fluctuations, the picture is more complicated, but yet still, when you do the event by event binning and averaging, you retain exactly the same picture that comes back out. So we tried to essentially reconstruct the experimental analysis as closely as we could, allowing for all the fluctuations that we know are there. And now the current hot off the presses stuff that I'm very, very eager to share with you guys, maybe even with even newer results than these, is the results of running this on top of an event by event 2+1D hydrodynamic background. And we see all of these event by event signatures, a bump that goes one way from one hot spot, a bump that goes another way from another hot spot. And we see significant contributions to this left-right deflection. The punchline is that we needed to know if the effect is measurable or not. And it seems like it is. It seems like even with very conservative estimates, that for jets in the neighborhood of 20 GeV, which is a nice sweet spot for the new sPHENIX detector, which is about to come online, that there the deflections are expected to be large on average, and that you should be able to measure this effect and then start to use it to obtain information about the tomography of the plasma. So we're continuing to work in this direction, but the biggest question that we had is, how can I establish if it's measurable or not? And now I think we've got enough of a realistic simulation to say we're getting several degree deflections. This should be a measurable effect. So we're very excited for the onset of sPHENIX. We're working very hard to make quantitative predictions that they can take and look for, hopefully establish a new set of observables that may be sensitive to the microscopics. Thank you for your patience. I'm sorry for running 100% over time.
Okay, super. So thank you very much again, Matt, for a great talk and for waking up early for us. You answered several questions during the talk, but let's throw the floor open for questions, any further questions that we might have. Yeah, I think Daniel wants to ask something.
It's probably a very silly question based on just this last idea of whether this event is measurable or not. So if we're expecting some sort of deflection based on the nuclear plasma medium that we were dealing with before, but have always been there, how would we distinguish this deflection
yes.
with the data?
Yeah, so very good. There are two ways that we talk about. I didn't have time to talk about that here, but there are essentially two ways that you could look for this effect. The simplest one is if you can fix the reaction plane. So if you use the event plane detector from STAR, or I think sPHENIX is going to inherit that, then basically you can keep the orientation of the event approximately constant within an experimental bin. So you can bin in centrality, you can bin on the direction of the reaction plane. If you have that, then you can just look at the angular modulation of the jets. Then you can just look at the angular distribution, and you can look at the cosine 2 theta moment of that. In the absence of a preferred direction, in the absence of a preferred direction, you shouldn't have anything that biases it to go left versus right. So, excuse me one second, this cat's gonna drive me crazy. Get out of here. Rush on the door the entire talk. Go. Sorry. Right. So the point here is about the net left-right deflection. So what we were looking here is the average direction of a jet that is initially going in some particular direction. So if I can make that binning, the simplest thing that I could look at would be, let's say, a photon and a jet. So I tag on the photon going one direction, so I know exactly what direction the jet was initially. And then I measure the direction of the jet. And I calculate for all jets with a given photon direction, what is the average direction? If in the absence of a velocity correction or a gradient correction, that average should be 0, because the jet is equally likely to deflect left or right relative to the photon. So the simplest way of doing that is to look at two particle correlations with a fixed event plane. If you can do that by having an event plane detector, I think that's the largest statistics that you'll get. If you don't have an event plane detector, then you have to work harder. You have to look at correlations. Then you can do it by looking at 3 particle correlations. You need essentially a photon or 1 particle to tell you the initial direction of the jet. You need the measured jet to tell you the final direction of the jet, and you need a 3rd quantity to tell you about the orientation of the event. So for that, you can just take the ordinary V2, the ordinary V2 of collective flow, which is a reflection of the preferred direction of all of those particles. So in our paper, we formulated it either as a 2-particle correlation with a fixed event plane, or as a 3-point correlation between a photon, a jet, and V2. Essentially, you define that correlation so that you're capturing it despite the fluctuating background, and then you can decompose that in terms of Fourier harmonics. So it's a bit of a long story, but I think those are the 2 ways that you can access this. I think the event plane method is going to be the most promising one, probably, but I'm not super familiar with the limitations of the detector itself. We're going to have to really get into those details when we try to make quantitative predictions for sPHENIX. Does that answer the question?
Yeah. Okay.
Okay, thanks.
Super. Any further questions? I think you exhausted us with all great information and answering all our questions during the talk. So maybe let's thank our speaker one last time.
Okay, thank you very much.
So thank you. Really appreciate it, Matt.
Thanks.
No
Matt.
problem. All right, see you next time, I guess.
Absolutely.
Take care. Thank you.
Cheers.